Okay. Can you actually see my screen?
Yes. Yes, we can.
Yeah, okay. Perfect.
Perfect.
Okay. So today I'm gonna try to talk. So first of all, I would like to thank the organizer for giving me this opportunity. This is great because I mean today I have like a chance to talk about what can go wrong when you work with higher dimensional isogenies and why is it really hard to work with these isogenies. So I don't know how it works, but feel free to interrupt me to ask me questions, or should I keep an eye on in the chat? I mean, yeah, I will try to keep an eye on the chat.
I'll keep an eye on the chat as well, and I'll interrupt you if we have a question.
Perfect. Okay, let me start then. So I said, oops, let me move this bar here. Okay. So the title of of this talk was higher dimensional isogenies. But before starting with complicated stuff, let's talk about the main objects of isogeny-based cryptography. Well, the main objects are basically elliptic curves and isogenies. What's an elliptic curve? So we have a field K, and just for simplicity, let's assume that the characteristic of this field is different from 2 and 3. So basically, we can define an elliptic curve over K as a curve E, given by this equation here, y squared is x cubed plus ax squared plus b. And these coefficients A and B are in K are defined over K. And also we have a distinguished point at infinity, that we are going to denote with this O infinity. Why do we need these extra points? So we can actually define an additional law. So we have 2 points, P and Q. To sum these points, we draw a line between these 2 points, and then we find the intersection of this curve with this line. And the result of this addition will be the inverse, the point whose y coordinate is the inverse to this intersection here. That's pretty easy. What about if you want to double the point? Rather than using like the line intersecting the 2 points, we just use the tangent line. So this is basically the group law on elliptic curves. The other main object of isogeny-based cryptography is indeed isogenies. So we are given two elliptic curves, E and E prime. So an isogeny over K is a non-constant rational map, which is also a group homomorphism, which also in practice means that we have like an homomorphism between groups. And this description here is really abstract, but we can give something a little bit more concrete, and that's what I'm gonna do like right now. So this is how isogenies appear in Sage. So we have an elliptic curve, E0, defined over a finite field of size 19. So the elliptic curve is defined by this equation, y squared is equal to x cubed plus x. Then also the other main property of isogenies is that their kernels are finite, and an isogeny is completely defined by their kernels. So and also another property of this isogenies is that the degree of this isogeny is the cardinality of the kernel of this isogeny. This is kind of always true, but for the sake of working with having like a cryptographic goal in mind, we are just gonna define like the degree of this isogeny in this way, even though it's not always true. But I want just to give like an overview of elliptic curves and isogenies, and then I will start with cryptographic applications. So coming back to the example, this isogeny, we can define an isogeny by the kernel of this isogeny. In this case, we are going to define an isogeny whose kernel is given by the group generated by the point whose coordinates are 0, 0. This isogeny can be defined, can be computed explicitly in Sage, for instance. And the image curve of this isogeny, so if this is our starting curve, the image curve will be given by y squared is equal to x cubed plus 15x. And actually, as I said, is a non-constant rational map, which means that we do have explicit equations for this rational map. And these equations are given in this way. This is kind of an explicit example. And also, we can also say that roughly to compute an isogeny, I mean, the complexity of computing an isogeny depends on the degree of the isogeny, and roughly we can say that it depends on the size of the kernel of this isogeny. Then once we define isogenies, we can also define endomorphisms. So an endomorphism of elliptic curve is just an isogeny from the curve E to itself. And then we denote by this notation and E, the set containing all endomorphism of E, and also we include the zero map. This is because, I mean, we want, in this way, the endomorphism ring of an elliptic curve is indeed a ring. And this endomorphism ring define also a class of elliptic curves that are used in isogeny-based cryptography. And these curves are called the supersingular curves. An elliptic curve E is said supersingular if the endomorphism ring of E is in non-commutative. These supersingular elliptic curves have nice properties that make them easy to work with when we compute isogenies, and these are the curves that are used mainly for isogeny-based crypto systems. Well, the most notable example of isogeny-based crypto system is actually SIDH. SIDH stands for Supersingular Isogeny Diffie-Hellman. This is a key exchange and was introduced by CFAIL, Zhao, and Plut in 2011. So let me just give like a rough overview of SIDH, like high-level overview on SIDH, and then starting from SIDH, I'm gonna try to see what we can do in higher dimension. So how does SIDH work? So we have a starting curve. This curve is 0, and this is a supersingular elliptic curve, the fan over of p squared. And the prime p that we use in this case is of cryptographic size, which means that it's big. And also we have other two coprime integers, a and b. And given these two coprime integers, we define the A torsion and B torsion. What's the A torsion of the starting curve is 0? It's the set of all points in it 0, such that if we multiply this point P 8 times, this is equal to the identity. And it's possible to prove that the A torsion of it 0 is isomorphic as a group to Z mod 8Z times Z mod 8Z, and similarly for E0B, so for the B torsion of E0. What does it mean? It means that the A torsion of E0 is basically a group of rank 2. So since it's a group of rank 2, we can actually define two generators. And for SIDH, we fix the two generators for the A torsion, and we call them PA and QA. And also we can fix two generators of the B torsion of E0, and we call them PB and QB. So pictorially, that's what we have. We have a starting elliptic curve, and we have some points on these elliptic curves. These points describe the A torsion and the B torsion of the starting curve. How does the key generation work? So since SIDH is basically a key exchange, we have two communication parties. Let's call them Alice and Bob. Alice's key pair is given by a secret key, which is denoted in red, which is basically an integer, and then a public key, which is denoted in green. So given this secret key SKA, Alice computes an isogeny, phi A, whose kernel is given by the subgroup generated by the point PA plus SKA QA. So Alice generates this isogeny phi A and then maps PB and QB, that are the generators of the B torsion under this secret isogeny here. And the public key will consist in the curve, the image curve EA, together with the images of PB and QB under this isogeny phi A. Bob does the same, and we have an analogous reasoning for Bob's key pair. So this is how the key generation works. So how do Bob and Alice share a secret? Well, so Alice starts from Bob's public key, which means like she takes like the elliptic curve EB and also phi B of QA and phi B of PA. And then she applies her secret key, SKA, which is an integer. And in this way, she computes another isogeny that I've called again phi A, because I mean, it's roughly, intuitively, we're just applying the same isogeny, but on a different starting curve. And Alice computes this isogeny, whose kernel is given by phi b PA plus SKA phi b QA. In this way, Alice ends up in this curve, EBA, and if Bob does the same, starting from Alice's public key, they will eventually end up in the same elliptic curve, which is actually the shared key. And this is a really nice idea. And so when I started my PhD, what I tried to do, I said, like, this is a really nice idea. What happens if we try to generalize it in dimension 2? Well, in dimension 2, it's possible to do so, because I mean, in dimension 2, we do have a group law. And this group law is kind of similar to the case of elliptic curves. So in dimension 2, we have two types of surfaces. We have elliptic products, which is basically a product of two elliptic curves, and we can consider it as like the group generated by like given two elliptic curves, E1 and E2. An elliptic product is basically E1 times E2 as a group. And the second class of surfaces is given by Jacobians of genus 2 hyperelliptic curves. This is a really abstract concept, but actually we can make it a little bit clearer just giving this pictorial description of the group law in dimension 2 for genus 2 hyperelliptic curves. So in this case, I mean, points on the Jacobian of a genus 2 hyperelliptic curve are given by, again, here I'm a little bit wishy-washy, but I just want to give like intuition for how the group law works in dimension 2. So points on the Jacobian are described by pairs of points over the genus 2 hyperelliptic curve. So assume that we want to sum up like this pair of points, P1 and P2, to Q1 and Q2. What do we do? So in the case of elliptic curves, we drew a line between the 2 points, and then we intersected like the elliptic curve and find the sum of these 2 points. In this case, rather than drawing a line, we draw a cubic, and we draw a cubic intersecting like the 4 points, P2, P1, P2, Q1, and Q2. Then we intersect the curve with, we find the intersection of this cubic with the genus 2 hyperelliptic curve. And this cubic intersects the genus 2 hyperelliptic curve in these points, minus R1 and minus R2. And as in the case of elliptic curves, the result of this group law, of this addition, will be given by the points whose y coordinates are the inverse of the previous ones. And so this is kind of analogous. I mean, this is kind of a nicer generalization. So we do have group law in dimension 2. What do we need? What do we need to define also to try to differentiate an SIDH in dimension 2? We also need to be able to compute isogenies. And the natural generalization of isogenies in dimension 2 is given by NN isogenies. What's an NN isogeny? Here I'm going to be a little bit vague on purpose, but we can say that an NN isogeny between surfaces is just an isogeny whose kernel is isomorphic to Z mod NZ times Z mod NZ. And there are algorithms to compute NN isogenies like kind of efficiently, and especially for 2-2 isogenies. I mean, the computation of 2-2 isogeny is extremely efficient. So we had all the ingredients to define SIDH, and indeed there was there already was a generalization of SIDH in dimension 2, and this generalization was described in the paper Genus 2 Isogenic Cryptography by Flynn and team. The main drawback of this idea was that it was not really practical, because I mean computing like 3-3 isogenies was a little bit too expensive, and so the protocol was really slow. So together with my supervisor, we said like, okay, so computing like my supervisor Chloe Martindale, we said like, okay, so computing like 3-3 isogenies is not really efficient, but computing 2-2 isogenies is efficient. I mean, we do know how to do that efficiently. But so to create this genus 2 SIDH, we need to compute 2-2 isogenies and 3-3 isogenies. What about if we stick to kind of the same type of isogenies for both Alice and Bob? So one of the possible answers to this problem was, rather than considering like NN isogenies, what happens if we consider cyclic isogenies? A cyclic N isogeny between surfaces is just an isogeny whose kernel is isomorphic to Z mod NZ. So what about if we try to use these isogenies to create like an SIDH key exchange in dimension 2? Well, the main reasoning behind that was the 2 isogenies are efficient to compute. So cyclic 2 isogeny should be even better to compute. Then I tried to create this an SIDH-like key exchange using 2 cyclic 2 isogenies, but I failed miserably. Because I mean, I couldn't find an algorithm efficient enough to compute a single cyclic isogeny. So for cyclic isogeny, like for n cyclic n isogeny, let's L be a prime. For a cyclic L isogeny, if L is bigger than 3, there is an algorithm to compute this cyclic isogeny. This algorithm is not efficient, and there is not a proper implementation of this algorithm. But even worse, for cyclic 2 isogenies, there was no implementation, no actual strategy to compute that isogeny. So I basically got stuck on this problem, and I said, like, okay, let's move on on a different topic. I spent actually almost a year just gaining knowledge in dimension 2 and what was the generalization of elliptic curves in dimension 2. So I said, like, let's use this knowledge to do something else. Then I went to Leuven for a visit, and I collaborated with Wouter Kastring and Thomas de Croo, and we stumbled upon this theorem called Canis criterion. This is kind of the criterion was not stated in this way. This is kind of the modern way of stating Canis criterion. But Canis criterion basically says this thing. So we have 2 isogenies, phi n1 and phi n2, both of them originating from E0, and phi n1 maps onto E1 and phi n2 maps on E2. And then the degrees of these 2 isogenies, that are called n1 and n2 respectively, are actually coprime. So once we have these isogenies, let's define this subgroup here, K, which is a subgroup of E1 times E2. This subgroup is generated by 2 generators. The first pair of points is given by n2 phi n1 p, n1 phi n2 p, and the second generator is similar to p, but rather than using similar to the first one, but rather than using p, we use q, and these p and q are actually the 2 generators of the n1 plus n2 torsion of E0. So once we define this subgroup here, K, then this subgroup here is like an n1 plus n2, n1 plus n2 isogeny in dimension 2, phi. We can compute actually an isogeny, an n1 plus n2, n1 plus n2 isogeny phi, having kernel K. And this isogeny here has this matrix form. So the first component of this 2-dimensional isogeny will be given by the dual of phi n1, and the second component minus the dual of phi n2. And then there are other 2 isogenies on the second row, gn2 and gn, and the dual of gn1. These gn i's isogeny are related to the f and i's isogenies in this way. So the composition of the dual of phi n1 with phi n2 is equal to gn2 composed with gn1. And okay, so this is like a really abstract theorem. Doesn't say much at the moment, but wait. Here we have like the image of some torsion under some isogeny. So if we are just given the image of some torsion under a certain isogeny, then this 2-dimensional isogeny will reveal the isogeny, the dual of the isogeny itself. So if we have just the image of some torsion, then we can retrieve the isogeny. itself, well, that was something that we already saw, like somewhere. And that was basically what SIDH was doing, was publishing the image of some of the 2 to the b torsion under like a secret isogeny. So then using Canis criterion, it's actually possible to attack SIDH. And that was one of the results that we obtained using the Canis criterion. So let me recall just briefly SIDH. In SIDH, we have the secret isogeny given by Bob, phi b. And then what does Bob do? Bob maps the 2 to the 8 torsion under this isogeny here. So if we compute another isogeny called phi extra, mapping another curve called E extra to E0, and we also map the 2 to the 8 torsion under this isogeny phi extra, well, if this isogeny phi extra is special in the sense that the degree of phi extra plus the degree of phi b is equal to the 2 to the a torsion is equal to 2 to the a, well, in that case, we can construct as in the using Canis criterion this nice isogeny here. And this nice isogeny here will have as first component this isogeny phi extra that we computed to attack SIDH. And the other component will be minus the dual of phi b, which was this, the secret isogeny computed by Bob. And that reveals the secret key of Bob. We can do the same for Alice. I mean, it's the same procedure. In this case, this isogeny phi, so this was a success, and we managed to attack SIDH. This is contained, this description of the attack is contained in the paper, Direct Key Recovery Attack on SIDH, which is joint work with Chloe Martindale, Lawrence Pani, Giacomo Pope, and Benjamin Wesolowski, and was also independently published by Walter Kastrik and Thomas De Croo in the paper An Efficient Key Recovery Attack on SIDH. One of the features of this isogeny phi is that it maps E extra times EB, these two isogenies, the product of these two elliptic curves, onto E0 times another curve that I've marked with E question mark. So for the attack, we just use like the first row of this two-dimensional isogeny. But what about if we analyze the entire information given by this isogeny here? I mean, it's just a waste if we just use the first row of this two-dimensional isogeny. And also, what's this curve here? Key question mark. Well, so I said like, well, maybe we can use it for another application. At a certain point, like in October, I just got COVID. So the first day I got COVID, I was like in my bed, I was sick. And the only thing I could think of was, okay, how can I compute efficiently an isogeny of degree 15? Why 15? Why the number 15? The number 15 is because 15 is equal to 3 times 5. And if you sum 3 plus 5, then you obtain 8, which is 2 to the third. So is there like an efficient way to compute this isogeny of degree 15? Well, there are like, first of all, how do you compute like an isogeny of degree 15? We can first compute an isogeny of degree 3 originating from E0, and then compute another isogeny of degree 5, and then we obtain this isogeny of degree 15. Or we can first compute an isogeny of degree 5, and then an isogeny of degree 3. Then, as I said before, t plus 5 is equal to 8, which is equal to 2 to the third. So if I just apply Canis criterion on these two, using these two isogenies, phi 3 and phi 5, then we have the two-dimensional isogeny having this kernel K will have these components here that, I mean, we computed them, so we already know those components. And we'll map E3 times E5 onto E0 times E15. What does it mean? That if I try to compute just in parallel the two isogenies phi 3 and phi 5, I can actually reconstruct this kernel K here. And from this kernel, I can compute a two-dimensional isogeny, which will reveal the curve E15. So, well, if this procedure doesn't need to compute the entire isogeny phi 15, but rather you compute two isogenies phi 3 and phi 5 in parallel, and then you can, using these two isogenies, the computation of these two isogenies, then you can reconstruct this kernel K, and from this kernel, you can actually compute the isogeny phi 15. So computing an isogeny in dimension 2 of degree 8 is quite efficient, because I mean, it just requires to compute 3 2-2 isogenies, and computing 2-2 isogenies is actually really fast. So potentially, there could be like, we could have achieved something to, I was thinking maybe we can achieve something to compute isogenies in parallel. I mean, we all know that computing like an isogeny, a prime degree isogeny, can be done like in parallel, because I mean the computation are almost perfectly parallelizable, so that's fine. But what about if we can actually compute square free isogenies of degree square free in parallel? And that was one of the ideas that I was trying to pursue. So in the example worked for 15, because I mean 15 was 3 times 5. But what about if we try to generalize it? So we start again. Let's this is just the first attempt to generalize this idea. We start from E0, a supersingular elliptic curve over Fp squared, and then we have this prime P given in this form. P is equal to the B times F, some cofactor F, times L1 times LR minus 1. And these LIs are distinct smallish primes, small primes, because I mean, whenever we compute, as I said, like in one of the first slides, roughly the complexity of computing an isogeny between elliptic curves depends on its degree. And so since we want to compute isogenies of degree Li, then if these primes are small enough, we have something that actually could be can be advantageous. So we have these primes here, Li's, all of them distinct and of course different from P. And then we have a point T on E0 of order L1 times the product of all the Li's. So right now our goal is to compute an isogeny whose kernel is given by the subgroup generated by T. And why I've used this notation phi P1 P2, because I mean, now I'm gonna explain what's the generalization that we can try to do. So let's suppose that there exist S1 and S2 to set subsets of all the primes Li's such that they partition the primes Li's in this way. So the intersection of S1 and S2 is empty, and the union of S1 and S2 gives back the set of all the Li's. And then let's define P1 and P2 in this way. P1 will be the product of all the primes in S1, and P2 will be all the product of all the primes in S2. And now, since we want to compute in parallel two isogenies of degree P1 and P2, let's assume that P1 and P2 are roughly the same size, so we have a balance. And what's the other condition that we need to apply? The other condition is that P1 plus P2 should be a power of 2. The sum of P1 and P2 should be equal to a power of 2. Well, if all these conditions apply, we compute in parallel an isogeny of degree P1, another isogeny of degree P2, and let's call them phi P1 and phi P2. And then we apply again Canis criterion using this kernel here. This is basically, I've used, rather than using the notation N1 and N1 and N2 as in Canis criterion, and when I stated the Canis criterion, I'm just using notation P1 and P2. In this way, we have an 2 to the B isogeny in dimension 2, which can be computed as a chain of 2 isogenies, which is really efficient. And this way, we are gonna, this two-dimensional isogeny having this kernel here will reveal to us the elliptic curve EP1, P2. So yeah, that's a nice way. I mean, if we have all these conditions, we can compute. We can actually hope to have something which is efficient. We can hope to have a strategy to compute isogenes in parallel. But actually, this condition here is a little bit. I mean, is hard to have like in practice. Because I mean, finding like products of small primes such that they sum up to a power of 2 is pretty rare. But actually, we can hope to have a little bit more leeway if we generalize it, and we introduce M1 and M2 to other integers, such that the first three conditions are basically the same as before, but the fourth condition will be this one. So M1 squared times P1 plus M2 squared times P2 is equal to a power of 2, is equal to 2 to the B. In this way, these integers here, M1 and M2, don't need to be smooth, because I mean, there's just a scalar multiplication that we're gonna do. So that can be anything. Then how do we compute this curve here? Well, as before, we compute an isogeny of degree P1 and another isogeny of degree P2 in parallel. And then we compute another isogeny, a two-dimensional isogeny, having this kernel here. This is just a straightforward kind of generalization. I mean, if you just do like a little bit of pen and paper maths using Canis criterion, you obtain, I mean, you can convince yourself this is the right kernel to compute. I'm just gonna save you from doing all these computations because I mean, they are a little bit dull. So in this way, we obtain again in 2 to the B isogeny in dimension 2. And computing this isogeny is actually a little bit, I mean, it's really efficient. Yeah, I mean, not really. It's efficient enough, let's say that. So what can we do with these isogenies in parallel? The first thing I thought was, oh, okay, maybe we can have like CSAD in parallel. What about, I mean, in CSAD, we need to compute at each step during whenever we need to compute like a group action, we need to compute this isogeny of square free degree at each step. So what about if we apply this idea to C-side? We tweak a little bit C-side and we try to apply this idea. I was still under the effect of COVID, so I tried to code something up and try to find nice values. And I came up with this nice example. I said yeah, this example is pretty nice. So we take like 15 small primes, we batch them in P1 and P2 in this way. Then we also have M1 and M2. And then all these values verify this nice condition here, which was optimistic. So I had like 15 primes and I managed to batch these primes in these two sets here, 3, 5, 11, 19, 53, 73, and so far and so on. So I said, okay, that's nice. But what about if I want more than 15 primes? Because I mean, 15 primes, I mean, this example is nice, is appealing to see, but nothing more than that. It's not practical for cryptographic applications. Well, when I tried to generalize this example, it happened to be actually, I should have expected that, but I had COVID, so I think that I'm excused for this kind of, for being too optimistic. Whenever we try to batch more primes, our quantity 2 to the B will explode. So the two isogenies that we need to compute to glue the curves together, we are going to compute so many of them that there's not going to be any advantage at all. I mean, I don't think that's going to be any advantage at all. So I got a little bit discouraged and I said like, okay, this is not something that I should try to do. But then sometime after I convinced myself this idea was rubbish, Andrea Basso joined our group like in Bristol, and he showed me this nice diagram. So it's pretty similar to SIDH. We start from and the elliptic curve, super singular elliptic curve is 0. Then we also have PB and QB, generators of some torsion over the some torsion on E0. Then we compute an isogeny phi A, and we map these points PB and QB under this isogeny phi A, and then we mask these points by a matrix A. What's the meaning of masking the points of under this matrix A? Well, so if this matrix has component alpha, beta, gamma, and delta, so when we mask the pair of points given by P1 and P2, masking this pair of points by this matrix is just what you will assume it will happen. So we just like the common matrix multiplication. So the first component, the first row will be given by alpha P1 plus beta P2, and the other row will be given by gamma P1 delta P2. As for the sake of clarity, there's nothing exotic going on in this slide. So let's come back. So we take these points here, we mask them by a matrix A, and we obtain two other points. Let's call them RA and SA. Then we compute other two isogenies, phi 1 and phi 2. The isogeny phi 1 will be originates from E0. The isogeny phi 2 originates from EA. And we do kind of the same procedure for phi 1. We take PB and QB. We map these points under the isogeny phi 1 and phi 1. And then we mask these points by B. And we do the same for phi 2, but we mask RA and SA, and then we map like RA and SA and mask these points by the same matrix B. Well, we have this nice diagram, because I mean, if we this diagram is actually nice, because when we consider the isogeny psi given by the dual of phi 1 composed with phi A composed with phi 2, which is basically an isogeny connecting E1 and E2. Well, in this way, we have this isogeny psi, and this isogeny psi is special because it verifies this nice condition here. So B, if the point, so when we consider the points psi R1, psi S1, and we mask them by the matrix B times A times the inverse of B, then we have the relation, then we have that this result is equal to R2 and S2 just scaled by the quantity degree of phi 1, which is quite nice. But if we furthermore assume that B and A commute, oops, wrong button, then we have this relation here, because I mean, B and A commute and B will cancel out with B, the inverse of B, which means that the image, the torsion R1 and S1, the image of R1 and S1 under psi is masked by the same matrix A, which has been used to mask the isogeny phi A, the points under the isogeny phi A, which is quite nice. Which means, what's one of the potential like applications that we can do with this nice diagram? Well, we can try to do like a trapdoor function. So phi A is our secret key together with A. So these are like parts of our secret key. The public key will be given by EA and RA and SA. And then to evaluate our trapdoor function, we just need to evaluate the two isogenies E0 and the two isogeny phi 1 and phi 2, and maps some points and mask them by the same matrix B. And then to basically to recover like the secret, to invert this trapdoor function, what does it mean? We need to recover the isogenies phi 1 and phi 2. To do so, we just take a look at the isogeny psi, and if we have access to our secret key A and phi A, we can actually have direct access to the image of some torsion under this isogeny psi. And then once we know how to compute psi, we recover psi using like SIDH attacks, we can actually recover these isogenies phi 1 and phi 2. The catch that we have here is that B and A should commute to each other, And hopefully we should not reveal anything of B or anything of A composed with B. I mean, like there should A and B should be somehow independent. So what we can do is that we can pick the class of matrices we can use. We can use like matrices such that they are diagonal, and diagonal matrices commute, or secant matrices. A secant matrix is just a matrix whose components are given by alpha, beta, beta, alpha. So having this, we have actually a nice diagram, and actually this is a nice idea to define a trapdoor function. And when I took a look at this picture here that he drew in front of me, I said like, okay, I mean, that was not the initial picture that he drew in front of me, but was somehow similar to this. I said like, okay, so maybe I have like an idea that I can apply to make this protocol work. So what we did is this one. Rather than having just this, the secret isogeny phi A is computed as we can imagine that we compute this isogeny phi A as like a composition of two isogenies, phi A1 and phi A2. Why am I splitting this isogeny? Now it will become clear. So I mean, imagine that we have a secret key. We have access to secret key phi A and the masking matrix A, and then given like the image of our trapdoor function. What's the image of our trapdoor function? E1 R1S1 and E2 R1 R2S2. We want to recover phi 1 and phi 2. What do we do? So first of all, let's call DAI the degree of phi I, which means that this isogeny we have degree DA1 and this other isogeny we have degree DA2. And then let's call DI the degree of phi I. So which means that phi 1 will have degree D1 and phi 2 will have degree D2. So we have these values here. And if we find some solutions for this, if we find some integers, M1 and M2, such that M1 squared times DA1 D1 plus M2 squared times DA2 D2 is equal to 2 to the B, well, we can apply the previous idea because, I mean, in this case, DAI times D1 will play the role of P1, and DA2 D2 will play the role of P2. Well, once we find solutions to this equation, we can actually take a look at these two isogenies, phi n1 and phi n2, given in this way. And using Canis criterion, as before, we construct this kernel here, which is given by, we take like R2 and S2, which is part of the image of our trapdoor function. Then we unmask these points by applying the inverse of A. We obtain a pair of points R2 prime, S2 prime. And then we construct this nice kernel here. And this kernel is just, I mean, once we construct this kernel here, you don't have to look at all the points here. You just need to understand that this kernel here depends uniquely on R1 and S1 and the points R2 prime, S2 prime. Then we can actually the isogeny having this kernel, the two-dimensional isogeny with this kernel K, will have these components here. And let's just take a look at the first component of this two-dimensional isogeny. The first component will be given by the dual of phi 1 composed with phi A1 composed with the scalar multiplication M1. Well, in this case, if I know the secret key, I know phi A1, so I can actually recover the dual of phi 1, which is basically equivalent to recovering phi 1. And for the second component, we can do the same. And knowing the dual of phi A2, we can actually recover phi 2. And this is like a nice way to invert our trapdoor function. So everything works, assuming that we can find some values here, verifying this equation. And if we relax again the idea that I described before to compute isogenies in parallel, we relax this idea to, rather than having like P1 and P2 to be square free, we have some values, some other integers here, positive integers. Well, we actually can find some values that I've stated here. These values, what's like the main feature of these values, D1, D2, DA1, and D2, they are extremely smooth. I mean, not extremely, they are smooth. And that means that they are the one-dimensional isogenies having degree D1, D2, DA1, and D2 are actually computable, and which means that the protocol becomes efficient enough. And these parameters and this idea is actually described in this paper here, FESTA, which stands for Fast Encryption from Supersingular Torsion Attacks. And this is joint work with Andrea Basso and Giacomo Pope. So this was kind of a nice way to apply the parallelization idea to obtain something different. So I was still a little bit satisfied. But, well, my main idea was that I wanted to achieve something like more efficient. I wanted to compute I wanted to compute something like in a more efficient way, but isogeny-based cryptography is not known to be like the fastest candidate amongst all the post-quantum candidates. Actually, maybe one of the main selling points of isogeny-based cryptography could be that it's kind of compact. I wouldn't say like the most compact one. It depends on the protocol. So but we don't need to be all the time fast. There are certain primitives that work when we have enough, when they are slow. I mean, we are after like the slowness of certain protocols. So what can we do? So far, we have analyzed this. I mean, this is the matrix that I've showed you before. This is the two-dimensional isogeny that I've basically put in every slide, in each slide. So we have some isogenies, phi1, phi n1, phi n2. What are the conditions that we have on these isogenies? Well, they must sum up to a power of 2. The isogeny phi n i, the isogeny phi n I should be efficiently computable. What does it mean? That the square free part of the degree n1 is smooth, which is actually basically like the case as in FESTA. And what was the other requirement that we had? That n1 and n2 are actually coprime. So in this case, we can compute efficiently this isogeny, two-dimensional isogeny here. But what about if one isogeny? So what about if one of the two isogenies used to create this two-dimensional isogeny is actually efficient to compute and the other one is not? So what about if, for instance, phi n1 is hard to compute, but phi n2 is not? Phi n2 is super fast to compute, efficient to compute. We can actually manipulate the degrees. We can actually tweak their degrees so we can have something we can work with. Can we use actually the two-dimensional isogeny phi to verify that an evaluator has honestly calculated the hard to compute isogeny phi n1? I mean, does it ring a bell? Are there any primitives that we can use with this idea? Well, one of the primitives that actually we can hope to construct using this idea is like delay encryption. Delay encryption used by Burge and DeFeo in the paper delay encryption. So with red now I will denote something which is hard to compute, and with blue I will denote something which is easy to compute. So let's assume that n1 and n2 sum up to a power of 2. Then what's the main goal of delay encryption? I encapsulate some secret. In this case, our secret can be the kernel of an isogeny, an efficient to compute isogeny phi n1. And then our ciphertext will be given by E2, this elliptic curve here, together with the image of some torsion under this isogeny phi n2. So the aim of delay encryption is that I encapsulate something, I encapsulate a secret, but to retrieve this secret, this secret cannot be decapsulated before like a certain prescribed amount of time. So how does it work? How does it work? We have this efficient to compute isogeny find 2. I encapsulate my secret key, and I provide to you this ciphertext here. Then to retrieve this isogeny, I need to run again the attack on SIDH, which implies that I need to reconstruct like Canis criterion, which requires me to compute. And how to given this constriction, I need to compute an isogeny of degree n1, and this isogeny is actually hard to compute because I mean I've picked the degree to be maybe not smooth. I've picked my prime to be of a specific form. And in that case, I can say that if you want to recover my isogeny, if you want to recover my kernel K, well, you need first to compute this isogeny here, and that's really hard to compute. We can actually bound the complexity of this isogeny, and then you can actually retrieve. So before having access to decapsulate my secret key K, you will need some time to do so. So let me summarize it again. The goal of this delay encryption is that recovering find2 cannot be faster than a certain fixed delay. Assume that we can do that. We can actually tweak our parameters such that we know that find1 cannot be computed by faster than a prescribed delay. Well, so this idea is nice. We can actually use not for the first time, we can use the slowness on an isogenies for good. But actually there is a problem. So the problem is that there are many ways to recover like a 2-dimension and 1-dimensional isogeny. I described just the way in which you restrict yourself to dimension 2, but actually, as showed by Damien Robert in his paper, Breaking SIDH in Polynomial Time, you can actually use an isogeny of dimension 4. In that case, you don't need to compute this hard-to-compute isogeny phi1. You just need to compute an efficient endomorphism in dimension 4, which is nice. I mean, you don't need to necessarily go through this delay, this burdening computation. But what's the catch here? I mean, the computation of the isogenies in dimension 4 is actually polynomial time, yes, but there is at the moment no concrete implementation of these isogenies. So maybe, I mean, the problem with this idea is that we can't estimate like the complexity of, we can't give like a precise estimate on, or actually lower bound on the delay that we should go through to retrieve our encapsulated isogeny. So, well, now delay encryption is not the only primitive which requires to be slow. There is also another primitive which is called verifiable delay function. As before, we have an isogeny with red the hard to compute stuff, and in blue the easy to compute stuff. So what we do in a verifiable delay function, the idea is pretty much the same, but in the verifiable delay function, a verifier wants to verify that a certain person, evaluator, did a burdening computation, like a really slow computation. So let me summarize it again. So now the aim is different. So first there is like an evaluator that computes this hard to compute isogeny phi n1, and then other people, other verifiers want to check that the evaluator did actually something hard to compute, that spent some computation, spent some energy, wasted actually some energy in computing like a huge isogeny. This idea is kind of nice. I mean, maybe we can use this idea to, delay encryption is hard to estimate, is hard to give like a precise description of that primitive, but maybe for a verifiable delay function, we can do something better. The problem with Canis criterion is that Canis criterion is completely oblivious to the isogeny phi1 we are using. The only thing that we need for Canis criterion is that the isogeny phi1 must have degree n1. So that's the only requirement. So how can we fix like the soundness of this protocol? Because I mean, potentially an evaluator can use like main isogenies of degree n1, and it will always, for the verifier, will always be the same. But how can we fix like the soundness of this protocol? One of the ideas that we described in this paper towards a quantum resistant weak verifiable delay function, which is joint work with Thomas De Croo and Antonio Sanso, was to use horizontal FP isogenies. So basically, we merged like the C-side scenario with like the attacks on SIDH, and we obtained this weak verifiable delay function. And this actually was like the main idea why we were trying to pursue with Thomas and Valder when we stumbled upon Canis criterion. And so we published this paper in Latin Crypt, and you can find like, I mean, this idea is not complete, is by any means complete. There are still, gaps that needs to be fixed, but we try to use like this slowness of isogenies for good in this way. Okay, so I think it's almost time. So let me just summarize. I mean, let's just tell you what are the things that keep me awake at night. So one of the things that I would like to keep on working on is the applications for parallel isogenies. Maybe there are other applications. The main reason why I discarded the idea is that I need to compute loads of 2-2 isogenies to actually glue the two curves together. But maybe, I mean, we know that computing 2-2 isogenies kind of is efficient, but not really efficient enough. But right now we have like new formulae for 2-2 isogenies, which are much better than the Richelieu isogenies used like for SIDH attacks. And just to give you like a rough estimates of the speed up that we obtain, the computation of evaluating an isogeny is 17 times faster than Richelieu isogenies, and computing a codomain of an 2-2 isogeny using this new technique, which relies on theta functions, is 9 times faster. This is actually some of the first result that we have. So we hope that we can actually have something nice. And this is ongoing joint work with Pierre D'Artois, Sabrina Kanzweiler, Giacomo Pope, and Damien Robert. So maybe using these ideas, we can actually save the computation for parallel. I mean, we can actually find an application. I mean, if 2-2 isogenies are fast, maybe we can find an application for parallel isogenies. Then I still want to find like a way to compute cyclic isogenies. That was mainly the initial idea for like that drove me to generalize C-side SIDH. That idea didn't work. At the moment, we have an alternative strategy to compute cyclic isogeny that also work in the case of two cyclic isogenies. And this is joint work with Chloe Martindale and Damien Robert. This idea is almost, I mean, there is still a problem with this idea. It's not complete. We still can't find like the last step to prove this algorithm. But this algorithm is not going to be fast, really. Maybe it's going to work, but not going to be fast. And another thing that we'll try to explore is like, there are some results on the polarizations of type 1-4 for principally polarized abelian surfaces, and these polarization come up when you compute like 2 cyclic 2 isogenies. So maybe, I don't know, something that I would like to explore and see what happens. And then the last thing is that find like precise estimates, or maybe also an implementation for like isogenies in dimension 4 to save like delay encryption, but also just to find like a concrete implementation of the attacks on SIDH in dimension 4. Basically, that's all for me.
All right, let's thank our speaker. All right, we have time for a few questions if anyone wants to come up to the mics in the room. I do have a question, which is that you describe all of this like very calmly from after the fact. But in the process of doing all this work, what was like the emotional high and low points of sort of making these discoveries?
Oh yeah. I mean, it was kind of, sometimes can be frustrating. I mean, especially when I tried to compute like cyclic 2 isogenies, that was really frustrated. And yeah, but then when we found out that we can actually attack like SIDH using that technique, that was really amazing. That was like a really nice feeling. So yeah, it was like an emotional roller coaster. I think that's almost like it's always the case. I mean, sometimes you just find some ideas that should work, and then you convince yourself that it should work, and then you're just thrilled, super happy. But then sometimes they don't work. I don't know.
All right, do we have any questions from the room? Okay, let's thank our speaker again. Okay, so we're going to break from lunch now. CFAIL will be returning at 2:45 today. Please take your bag.